All right, this week's lecture is going to focus on a very key important topic, and that is looking at two things. The different types of elements and what they can be classified on the periodic table, which for those of you that attended class last week in person, we've already kind of talked about that. Those of you who haven't, this is something that will be maybe review. If not, we'll go over it. But the second thing is these properties that we're going to investigate as I go across the periodic table or if I go down the periodic table. And when we say across the periodic table, for the sake of this unit, across is always going to be going across left to right, across the period. When I say down the periodic table, that's going to mean going top down, okay? Top down. So from the lowest energy level, which is the first row, all the way down to the very bottom seventh row, top down, what happens to these properties we're going to investigate today. Okay? All right. First of all, let's review. Elements can be classified as either a metal, a nonmetal, or a metalloid. Properties of metals are that they're shiny, they're almost all solids. The only one that isn't is mercury at room temperature. They are very conductive. They're conductive of heat of electricity. They're ductile, which means they can be drawn into wires. They're malleable, which means they can be pounded into a shape. And they are left of the staircase. Again, you may want to, on your chem helper, to draw in the staircase, which I've done it here in red, which starts at boron and goes all the way down between aluminum silicon, all the way down, finally between PO and AT. Any element that is on this staircase are metalloids except for aluminum. Aluminum is a metal. Okay? It's the only element on the staircase that is not a metalloid. It fits all the properties that make metals metals. Okay? But any element to the left of the staircase, including the F block down here, these are all to the left of the staircase. These are all metals. Again, there's always exceptions. The exception, obviously, is hydrogen. Hydrogen is the only element left of the staircase, so I guess hydrogen and aluminum. Excuse me, hydrogen is the only element, my fault. Hydrogen is the only element left of the staircase that is a nonmetal. Okay? But all other elements left of the staircase are metals. Nonmetals are exactly the opposite. They're dull. They tend not to be shiny. They're all different states. We have solids, liquids, and gases. They're not conductive, they're not ductile, they're not malleable, and they're right of the staircase. Metalloids, for the most part, it depends. Some are, they're all solids. Some are shiny, some are not. Some are conductive, some are not. The main thing is they tend to have a few properties of each, which makes them, again, like what a metalloid is. They are that shift between becoming a metal to a nonmetal. One of the key things about metalloids that you might want to just jot down is that they are semiconductors. They only conduct in certain set conditions, okay, which makes them very useful. All right, the second concept of today is looking at these trends on the periodic table. The first trend is the size of the atom, how big it is, specifically not mass-wise, but by overall volume, okay, how large it is, how much space it occupies, okay? And if this is the general shape of the periodic table, this box, as I go across the period from left to right, the atomic radius, which I'll abbreviate RI, AR, it gets smaller. As we go across the period, the elements get smaller and smaller. Even though they have more protons, electrons, and neutrons, they have more and more subatomic particles, which would mean you'd expect it to get larger, but it doesn't. It actually gets smaller. As you go down a family, the atomic radius, the volume of the atom, does get larger, which is to be expected. Students usually don't struggle with that one. The farther down you go, top down, the bigger and bigger they get. The key question is, why do they get smaller going across, even though they have more subatomic particles? The key concept is called Coulombic attraction. Now I'm going to turn the page here just to get to a piece of white here. All right, so if you are asked why do the atoms get smaller volume-wise when I go across? Why do the radiuses, the distance from the nucleus to the valence electrons, why does it decrease? The reason why is the Coulombic attraction increases. When I go across the period, the Coulombic attraction increases because there are more protons in the nucleus. There is a greater nuclear charge. and that causes the atom to be smaller. When I go down a family, the distance between the valence electrons and the nucleus is greater, and that causes a drop in the Coulombic attraction. There's a weaker attraction of the nucleus to the valence electrons, and because the valence electrons are more weakly attracted to nucleus, the atom is larger. All right? Ionic radius is looking at the sizes of an ion compared to an atom. Okay? Now again, we can have two types of ions. We can lose electrons, which makes it a cation, or we could gain electrons, which would make it an anion. Okay? The general rule of thumb is that if I have a cation, like sodium, the sodium plus 1 ion, where I've lost 1 electron, and then I have the sodium atom. When we lose electrons, do you think the atom is getting bigger or smaller? Well, where do we lose electrons from most likely? The outermost electrons are the ones that are going to be lost first. And if I lose them, the atom is going to get significantly smaller. So, cations are always smaller than atoms. Okay? Vice versa for anions. If I have the sulfide -2 ion, they are always bigger than their atoms. And that's because they've gained electrons. And when you gain electrons, you end up having more electron repulsion, and that causes the atom to get even larger. So anions are always bigger than atoms, and cations are always smaller. Now sometimes you can have an element that has multiple different charge states where they've lost different amount of electrons. Iron can have a +2 charge. It can also have a +3 charge. This iron +2 has lost 2, and iron 3 has lost 3. Who do you think is going to be bigger? You're correct. The more electrons you lose, the smaller and smaller it gets. All right? One other thing with size, and that's called an isoelectronic series. An isoelectronic series is a group of either atoms or ions in which all the particles have the same number of electrons. Okay? So here if we look at this group, neon, fluorine, magnesium, and aluminum. Neon has got 10 electrons. Fluoride, -1. Fluorine has got 9, but by being -1, it's gained 1. It has 10 electrons. Magnesium typically has 12, but being +2, a cation, it has lost 2. It's got 10. Aluminum typically has 13, but it's lost 3. So you'll see that they all have the same number of electrons. So then the misconception is students think that they're all the same size. They're not. Why? Coulombic attraction. What's going to cause there to be a different Coulombic attraction? Well, the number of inner shell electrons and valence electrons is not going to change because they all have the same number of electrons. The key is the protons. Neon has got 10 protons in the nucleus. Fluorine has got 9. Magnesium has got 12. Aluminum has got 13. So think of the nucleus and how much pull they have. Aluminum having 13 protons is going to have a greater pull on the 10 electrons than what the fluorine pull is going to have with only 9. Therefore, the more protons it has, the smaller the particle will be because it has a greater Coulombic attraction. Therefore, the smallest particle in this series would be aluminum because it has the most protons. Its nucleus has got the strongest pull, making the electron cloud smaller and smaller. Then comes magnesium, then comes neon, and lastly fluoride. The F-1 ion is the largest. They all have the same number of electrons, but fluoride is the largest because it has the lowest nuclear charge. Okay? A couple other concepts real quickly to wrap this up, and that is ionization energy. Ionization energy is the amount of energy it takes to remove an electron from an element. So down here, sodium, to become a +1 ion, it has lost 1 electron. Well, in order to lose an electron, there has to be energy given to it. So the question becomes, how much energy is needed to remove that electron? Okay, so the higher the ionization energy, that tells me that it takes more energy to remove that electron. Okay, well, what do we see? The data when we look at elements is when I go across the period, the ionization energy values increase, which means it takes more and more energy to ionize elements the farther right you go. Okay, neon has the largest ionization energy in the second row. Lithium has got the smallest. When you go across a period, it takes more and more energy to remove the first electron from an element. So the energy to remove lithium's first electron is much less than to remove neon's first electron. Okay? Now, why is that? Again, the why will always be answered in the same way. That's what makes it very nice. The coulombic attraction is greater when we go across the period. If there's greater attraction of the electrons to the nucleus, that's going to cause there to be a larger ionization energy. If there's more attraction, it's going to take more energy to remove the electron from the element. And again, we are looking at all of the same electrons. You're looking at the outermost electron for that element. Okay? Going down, the ionization energies decrease. They get smaller. Therefore, it's easier to remove an electron from an element the farther down the table you get. Why? Again, coulombic attraction. When you go down a family, coulombic attraction decreases. The electrons are farther from the nucleus. There are more inner shell electrons. The element is just bigger in general. And because of that larger size, it takes less energy to ionize the element because the electrons are farther from the nucleus. Okay? Ionization energy. The first ionization energy is the amount of energy it takes to remove the first electron. Yes. When I go across, the values get smaller. Ionization, larger. Atomic radius. When I go down, they get larger. When I go down for ionization, smaller. Coulombic attraction, this was from the POGL that you were supposed to do last week, and hopefully by doing that POGL you've gained a good appreciation for what coulombic attraction is. Coulombic attraction is the attraction between unlike charges. Positives and negatives attract to one another. And specifically in atoms, which we're talking about here, elements, atoms of elements, the protons in the nucleus are attracted to the electrons. And the more attraction they have, the more coulombic attraction they have. And specifically, the attraction we're going to most look at is the attraction of the valence electrons. The electrons that are on the outermost energy level, farthest from the nucleus. How much attraction do they have towards the nucleus? Okay? There are three variables that affects coulombic attraction. The first is the number of protons in a nucleus. The more protons you have, the greater the coulombic attraction is because the nucleus has got a stronger nuclear charge. This is called the nuclear charge effect. Because the nucleuses are charged, think of the nucleus as a magnet. The more protons in the nucleus, the more magnetic pull the nucleus has. The second variable is the distance the electrons are from the nucleus. As electrons get further and further away from the nucleus in higher and higher energy levels, as that distance grows, the coulombic attraction weakens. The farther two unlike charges are away from each other, the less attraction they have because of the distance. So that decreases the coulombic attraction force, distance. Okay? And lastly, the third effect is more of not a major, it's more of a minor one, but it does add into the decrease of coulombic attraction, and that is the inner shell electrons. The electrons that are in the energy levels inside of the valence energy shell, the valence row, these electrons repel the valence electrons, and that weakens the coulombic attraction of the nucleus to the valence electrons. So 2 and 3 decrease the coulombic attraction while number 1 increases it. So why does the atomic radius get smaller across? Well, the reason why is when I go across the period, Coulombic attraction increases. And if the nucleus pulls on the electrons, or the attraction of the valence electrons to the nucleus is greater, that is going, just like a magnet, the stronger the magnet, the more closer they're going to draw in and pull in. They're going to be pulled in towards the nucleus because of the stronger Coulombic attraction. Well, why is that? And that's because of the first variable. When I go across the period, the valence electrons are in the same energy level. They're all being put, let's say it's an element in the third row. They're all being placed in row 3. So the distance between the valence electrons and the nucleus is not changing very much. That is going to cause a decrease, okay, in the, because they're being placed in the same energy level, there really is not a drop in Coulombic attraction because they are in the same energy level. Also, when we go across the period, we are just simply adding electrons to the valence shell. We are not adding any electrons in the inner shells. Therefore, the number of inner shell electrons is constant. So both variables, 2 and 3, are pretty much staying constant. They're not really being affected at all. The only variable that is significantly changing is the number of electrons, a number of protons in the nucleus. So the distance and the number of inner shell electrons is not changing. Factors 2 and 3 are constant. So the only factor or variable changing as I go across the period is the number of protons. Therefore, there's more protons in the nucleus. The nucleus has got a stronger pull, and that causes the valence electrons to be drawn inward, making the atom smaller. When I go down a family, the number of protons is increasing. However, we have two variables that are also changing, and that is when I go down an energy level, the distance between the valence electrons and the nucleus is getting greater. Also, when I go down a family, there are more and more inner shell electrons, which causes a further reduction in Coulombic attraction. So now, when I go down a family, variables 2 and 3 together end up becoming greater than factor 1. And therefore, there is a decrease in Coulombic attraction when I go down a family, because of both factors 2 and 3 trump factor 1. Okay? And also we find out that the distance variable is a square term, which means distance has a very big effect on Coulombic attraction. The farther they are away, the more and more decrease there is in the attraction. So if you can understand this bottom of this page, this will really explain all the trends I'm going to talk about now. So I'm going to go back. One other thing about ionization energies, and that is successive ionizations. The last table we were looking at is called the first. Successive ionization energies are when we remove the second electron and the third electron. You'll notice magnesium, when it loses the first electron, it becomes +1. Well, when it loses the second electron, the +1 now becomes a +2. As we lose more and more electrons, the charge increases by 1 because we keep removing more and more electrons, leaving a more positive ion behind. What does the data show us? As we go from one ionization to the next, it takes more and more energy to remove the electrons. Why? The big reason why is when I remove electrons, we're removing electrons from the outermost energy level first. So as we remove the outermost, every time we remove, we're getting closer and closer to the nucleus. And therefore, electrons closer to the nucleus are more strongly bound to the nucleus. Therefore, they're harder to ionize. It's harder to remove them when there's a greater Coulombic attraction because they're closer to the nucleus. The last trend to wrap up today's lecture is electronegativity. Electronegativity is the ability of an element to attract electrons. When we go across the periodic table, electronegativity values increase. Again, why? Coulombic attraction increases. The nucleus has got a greater effect, okay? And it's got more protons in the nucleus. When you go across the period, the valence electrons are in the same energy level, and therefore, since the nucleus has got a greater Coulombic attraction, it is able to draw in more electrons, more valence electrons. There is one exception here, however, and that is group 18. Group 18 is the farthest or most right group. We exclude this group from this property. Okay? These guys tend to have electronegativities that's about 0, and that's because even though group 18 has got the greatest Coulombic attraction values, they don't want to attract electrons. Why? They're already full. And since they're already full, while they have great Coulombic attraction, there is no need to gain electrons because they already have the most stable configuration, which is a full energy level. So in this trend, you just have to remember that group 18 is voided, and I won't even ask questions about it, but understand that they increase across until we get to group 18, and then they tend to be 0. Lastly, when we go down a group, electronegativities tend to decrease. Okay, and again, why? Because the Coulombic attraction decreases. There's less attraction to the nucleus, and therefore it's a lot harder to attract electrons when they have very low Coulombic attraction values. Now, for this test, you have to know not also what each of these are, what an ionization energy is, what electronegativity is. You also have to know the trends. When you go across, what happens? When you go down, what happens? Now, if you look at the 3 trends we talked about, you'll notice that atomic electronegativity larger, go down smaller. So one way to remember this, and I tell students this, is the atomic radius trends is the unique trend. The other trends all perfectly match. Ionization energies and electronegativities increase when we go across, and they decrease when they go down. The atomic radius is exactly opposite. So if you can remember the atomic radius, all you have to remember then is all the other trends are exactly opposite it. Okay? One last type of question I might ask you is, for example, electronegativity, which element has got the greatest electronegativity? Well, this really is a trend question, but an application of the trend question, which makes it a lot harder. Not only have to know the trend, you have to be able to apply it. Well, if I go across, they get bigger. If they go down, they get smaller. The largest values are going to be in the upper right-hand corner. Well, which element is in the upper right-hand corner of the periodic table? Well, right away, some of you might say helium, but it can't be helium. Why? Well, you have to remember that helium is a noble gas, and noble gases already have full valence electrons. Therefore, if I get rid of group 18 in electronegativity, which element now is in the upper right-hand corner if we get rid of and cover up group 18? And the answer is fluorine. Fluorine has got the highest electronegativity value because it is in the upper right-hand corner, and they increase across and they decrease going down. Which element has the lowest? And if you said francium, you are correct. The element in the bottom left-hand corner would have the lowest value because they get smaller going down and bigger going across. So the smallest electronegativity would come from francium. So the elements that tend to have the biggest and the smallest tend to be in opposite corners of the periodic table. So you might also be asked questions like that in your homework or your quiz. Which element of the 4 has got the largest or the smallest? And again, there you have to be able to apply the trends of these different various properties of elements. And if you know the trends, you should be able to identify which element is furthest to that corner or farthest from that corner. Okay? So that's where the homework will come in handy. Very important that you do it this week and you get practice being able to practice these trends and predict which elements have got the highest or smallest values. Thanks for listening.